Alright, so we're back for the last video from exam 3, and this is talking about the solubility of gold 3 hydroxide in pure water and then in a 1.2 molar nitric acid solution. So, this I think is the hardest question on the exam because you have to understand that the gold 3 hydroxide is dissolving. It's barely soluble. You can see this tiny equilibrium constant here. It's dissolving in water where water itself has a common ion. And so we'll go ahead and dive into that, but you can expect that this is going to be a little bit of a hairy situation. It's not as bad to work out as it seems, but it's certainly hard to think about, I think, to realize everything that's going on there. So let's just dive in. So we've got gold 3 hydroxide. That would be Au. It's a 3+, so we need 3 hydroxide ions like that, and it's going to be dissolving. So when it dissolves, you get the gold 3+ ion, aqueous, and you get 3 hydroxide ions, also aqueous. All right, so here's the crazy thing, though. Before any of this dissolves, there's a significant amount of hydroxide compared to how much is going to dissolve. Remember, in neutral water, in completely, oh, I'm having a focus issue. There we go, we're back. In completely neutral water, water splits up all on its own into hydronium and hydroxide ions. And so in completely neutral water, this one is 10 to the negative 7 molarity, and this one is 10 to the negative 7 molarity. Now, if you compare how much hydroxide there is in that completely neutral solution of water to what the size of the equilibrium constant, you see that this is actually a significant amount of hydroxide compared to how much gold hydroxide may eventually dissolve. So we can't ignore this amount of hydroxide in the neutral water. So if we're going to do an equilibrium calculation here, we need to start out and say initially there's no gold in the water, but there is initially 10 to the negative 7 molarity of the hydroxide. Then, to the extent that gold hydroxide dissolves, we're going to add this, and we're going to add 3 times as much as this. And we just switch, instead of using x's, we use s's here because it's solubility. But you could still use x's there if you wanted in your sort of ice table format. So at equilibrium then, the concentration of this is going to be S, and this is going to be 10 to the negative 7 plus 3S. So let's go ahead and then write our equilibrium constant expression. KSP for this, the solubility product constant, or the equilibrium constant of this reaction, is just going to be the gold molarity times the hydroxide molarity to the 3rd power. And that's it. We don't include the gold hydroxide because it's a solid. It's not mixed in with the water in this reaction, so it's not part of the equilibrium. So now we just need to plug these in, and the equilibrium concentrations, and we can solve from there. So KSP is 5.5 times 10 to the negative 46. The concentration of gold 3 we'll call S, and the concentration of hydroxide is 10 to the negative 7 plus 3S cubed. If you solve this, then you'll get 5.5 times 10 to the negative 25 molarity for your solubility. And that's it. One interesting note here, though, is that you could have solved this exact same equation. It would have turned out the same way if you had just plugged in 5.5 times 10 to the negative 46 equals S times 10 to the negative 7. What we're saying is the amount of hydroxide in the solution was so big that the amount of extra hydroxide added wasn't a significant contribution. So you would have actually solved for that exact same number if you had used the S S is small approximation here, that the new amount of hydroxide dissolving is not a significant contribution to that. Would give you this exact same answer. And that simplifies it a lot. You can just divide it by 10 to the negative some cubed, which is 10 to the negative 21 over there, and you get 10 to the negative 25. Now we want to repeat that exact same thing, but we're in a 1.2 molarity nitric acid solution now. And the difference there is that instead of 10 to the negative 7 and 10 to the negative 7, we're going to have a much, much, much lower hydroxide concentration. So you can remember that the hydronium ion concentration times the hydroxide ion concentration in water is always 10 to the negative 14, as long as the water is roughly around 25 degrees Celsius. So that's how we got 10 to the negative 7 times 10 to the negative 7 is 10 to the negative 14 in neutral water. But in 1.2 molarity nitric acid, that's saying it's a strong acid, so it's going to dissociate completely. So that's saying the hydronium ion concentration here is 1.2 molarity. So you could plug in 1.2 molarity here and solve for the hydroxide ion concentration. And you'll get the hydroxide ion concentration now is much, much, much lower. So you'll get 8.33 times 10 to the negative 15. So where in neutral water it was 10 to the negative 7, now it's 10 to the negative 15. It's much, much, much lower. So you can then do that exact same setup. You take your gold 3 hydroxide. It's dissolving to give you gold 3 ions and hydroxide ions. You're going to start out with 0 of that. You're going to start out with not 10 to the negative 7 like we had up here, but you're going to get 10 to 8.33 times 10 to the negative 15. We'll already do that, plus S plus 3S to give you S, and 8.33 times 10 to the negative 15 plus 3S. Go straight to your equilibrium constant expression. KSP equals the concentration of gold 3 plus times hydroxide cubed. So same KSP, 5.5 times 10 to the negative 46 equals S times 8.33 times 10 to the negative 15 plus 3S cubed. Plug that into your calculator, do the math, and you'll get that the solubility is equal to 2.12 times 10 to the negative 12 molarity here. So in this solution, you can dissolve significantly more, times 10 to the negative 12 molarity gold hydroxide, than you could in the original neutral water solution, which would be times 10 to the negative 25. It's still not a ton because gold hydroxide is very, very insoluble, but it's more, billions more than it was back there. More than billions more. But here's another interesting thing. Here, it turns out, see how big that number is? It's times 10 to the negative 12. So this is much bigger than that number, than the amount of hydroxide. So we actually could have gone here and made an approximately 0 approximation to begin this calculation. If you had done 5.5 times 10 to the negative 46 equals S times 3S cubed, so you had just eliminated the initial amount of hydroxide, you would have calculated that exact same number right there. So if you could have actually shortened this calculation, being able to understand here that the amount of solubility was going to be so much less than the initial amount of hydroxide. And here, by adding a strong acid solution, we had made the initial amount of hydroxide so low that it wasn't significant compared to the amount of gold hydroxide that would dissolve. So that's it. There's your two answers. It's quite a complex solution. That's why I like doing it for partial credit, because if you had gotten one of the alternate answers for either one, I would have given you at least half credit for that. Thanks for watching.